And thank you so much for the invitation, the whole organizing team. Looking at Sarah because she's in front of me, oh, several of them right in front of me. So, I'm looking forward to this whole workshop and this whole conference. Rest of the conference is vacation because I will be done with talking, right? The title of the talk is Playing, Designing, Adapting, the Many Roles of Reinforcement Learning in Games. The point of this talk is not to talk to you about a particular benchmark or a particular method or particular anything. I just want to sort of, open your mind. So here's some psychedelics. No, but basically, he's trying to make you see how many interesting reinforcement learning problems there really are in games, in particular video games. So I'm at New York University. I'm also a co-founder of modl.ai, which is a game testing company. And I'm a guest professor at the University of Skövde in Sweden. You will not be able to pronounce that word. I'm from Sweden originally. I finished high school. I barely passed mathematics, did absolutely not want to go to engineering school because that would be, that's for boring people and there's a lot of maths, and look where I ended up. I still don't know any maths, but I'm a professor at an engineering school. In between, I studied philosophy, psychology, did AI in various places. I worked in Jürgen Schmidhuber's team together with Tom over there back in the day. And I sort of found my niche in AI for games and games for AI. And I've done a lot of work on playing games, some work on modeling players, a bunch of work on this and that. And most of the work I've done that someone cared about was about AI for designing games and game levels and so on. Enough about me. So Sutton and Bartow. Immediately switch to Sutton and Bartow. The definition of reinforcement learning in the first edition of the famous book is that reinforcement learning is defined not by characterizing learning methods, but characterizing a learning problem. Any method is well suited to solving that problem, we consider to be a reinforcement learning method. I think this is an important statement because this allows us to focus on the problem and then choosing widely among the very large variety of methods that could potentially solve these kind of reinforcement learning problems. And reinforcement learning problems, as you know, it's about something that we might call an agent interacting with something we call an environment, receiving observations and rewards, and learning from these observations and rewards, and taking actions. So here we'll talk about three types of problems in games. Playing, so playing well, playing in styles, and playing in general. Designing, levels, quests, characters, whole games perhaps, many different things. And adapting, appearance, ads, whole games perhaps, which I consider all to things you can fruitfully see as reinforcement learning problems. Let's start with playing. I'm going to devote exactly one slide to this stuff. You all know this stuff. You're in the workshop on reinforcement learning and games. And there's been a lot of research over the last 10 years, but I'm lying. There's been a lot of research over the last 40 years or so on reinforcement learning in games. And there's been a bunch of really strong sort of, I guess the real there's been a lot of good research on reinforcement learning in games over the last 60 years since Samuel's checker player. That's actually more than 60 years, but you get the drift. And then 10 years ago, we had the DeepMind's Atari DQN work, and then there's been a lot of follow-up work. We're going to hear about some of it here, including the Gran Turismo and other things. What they tend to have in common is that they use reinforcement learning to train one network to play one game in one style. There are exceptions to this, but this is the general gist of this. And I think that this is good and all good and nice, and we're not done with this yet. There are lots of games we can't play this way yet, but we're kind of done. This is perhaps not where the real interesting stuff is. One of the really interesting stuff is generalization. Having one model that can play not just one game, but like different versions of one game, or perhaps many different games. I was planning to have a few slides on this, but then I figured out that this is its own rabbit hole, and I don't actually know where the state of the art is here at the moment. This is something that I would love to bring up for discussion later on, but suffice to say that there is not like a reinforcement learned network that you can bring out there that can play a wide variety of video games without further tuning, or even, as far as I know, the one that can play all the Atari games well. There are, as far as I know, some that can play all the Atari games to some low standard, but not super well. But this is something that I would like to bring up a further further discussion, but this is definitely one of the frontiers. And one reason why we don't see much research on this is that it's extremely expensive, and it's hard to get all the test beds, and it's extremely expensive. The other frontier here that we see much less of is playing in style. So I am deliberately giving an old reference here because I like doing these kind of things. This is actually original references from the 80s. Richard Bartle's Typology of Player Types, which originally came from like a bulletin board message in sometime in the early 80s, where he divides player types into killers, achievers, socializers, and explorers. There's been a lot of work in game studies and HCR for games and in player experience modeling on trying to sort of figure out how do people play games, how do their playing style vary. Some of it is game general, much of it is game specific. What I have not seen is reinforcement learning trained agents, or even reinforcement learning trained and supervised fine-tune agents that can play any interesting video games in a wide variety of styles. Why is this relevant? Isn't games just about winning? No, not if you make games. Then winning is the least interesting part. Then what you're interested in providing interesting teammates, interesting opponents, interesting different agents that can help you test the game, and so on. And I've done some work on this in the past, but these are like old and ugly slides I didn't want to show you. But you can definitely do this by specifying reward functions that take into account very specific parts of player behavior, or you could use some loss metric between play traces of some player and what your agent does. But there's a lot of unexplored area here as well. Okay, slight sidetrack, because today is the day. Today is about neural game engines. I'll get to that in 2 slides. Neural game engines. So there is a line of research on trying to build neural game engines, also called world models, that are models that render a game or a world simulation in a way that you can, for example, play it yourself by issuing real-time commands, or having a reinforcement learning model play it. So a standout paper was from David Ha and Jürgen Schmidhuber back in 2018, where they had essentially LSTMs and autoencoders, and they trained networks to reproduce a simple 2D driving game and also a version of Doom. And they showed that you could train reinforcement learning agents that could play these games to some extent, not super well, but that they did it all entirely in simulation. So they were not training on the real game, they were training it entirely in simulation. The world was just a neural network. This was super cool. A lot of people kept working on this. The Dreamer series of models is sort of inspired by this. And there was a paper last year called Diffusion Models are Real-Time Game Engines. And the model was called Game Engine from a team at Google DeepMind, where they trained a diffusion model to render the game Doom. And this is very cool. Basically, this is the original Doom from '93, I think it is. And they had a reinforcement learning agent learn to play it. And they played it for a long time to generate lots of data. And then they trained this network to recreate it. So basically, you have like the WASD inputs and whatever other buttons you use for, just like a handful of buttons you use for Doom. And when this came out, I know that some people in the game industry sat up straight and like, whoa, what is happening here? you mean that this this game is all taking place inside a neural network? What is this? What does this mean for us? Does this is this going to take over the game industry or something like this? It's not taking over the game industry, at least in that sense, but it has a lot of interesting potential outcomes. First thing to note here is that this is just one game. And if you look at these videos for a few times, you'll notice a couple of interesting things. For example, it doesn't have much of memory. In fact, if you play Doom as implemented in this neural network, and you meet this evil enemy that is going to kill you, you know what the best thing you can do is? Turn around, look away, and turn back. Chances is that he's not there anymore. And this is how I approach life. But it's just one game. So what came out today, another team at Google DeepMind, well, some of the same team actually, released Genie 3, which is a promptable world model, also known as a neural game engine, that is very cool. It generates real-time, high-resolution videos, and you can play them of sorts. You can sort of use WASD and arrow keys and jump to move around, and you can often control a character. You can also do other things. And if you prompt it with something like, you know, a racing game where I drive a Ferrari through Greenwich Village, then you get that. And it's not a good game. It has issues. It decoheres at some point, but it kind of works, and that's really cool. And the visuals are great. You know, it looks awesome. There's a lot of stuff you can do with this. I just put out a blog post where I put out some ideas about what this means. I think for right now, I see this as an ideation tool. What you saw here was actually, I prompted this with Tetris, real life photorealistic, which is kind of an oxymoronic prompt. It's bizarre, and you get this bizarre thing, but it's very evocative. It's like, it's a game you may want to implement in a real game engine at some point. This idea with these game engines, let's just like focus on this for a few slides, and we get back to other use cases of RL. There are many things you can ask. One is, where does all the training data come from? And that's something you probably should ask before you, well, that is probably why this is not released publicly yet. Are the neural game engines actually more efficient than regular game engines? At the moment, no. In the future, maybe, who knows? Will they ever be reliable and coherent? Interesting question, I don't know the answer. Probably at some point. How do you author for or in a neural game engine? And that is the real big question. This talk is not about that, but just like sticking with this for a few slides here. So just to note that if you have ever tried to interface your AI solution, such as a reinforcement learning neural network, to a game engine, you will notice that regular game engine has some real problems because they were not made for this. One of the big things is that there's no fast-forward simulation. One of the reasons why Atari has been so popular is you can run it in real time, like you can run it in like thousands of times faster than real time in many threads on the same CPU. It's super great. Same thing for original Doom. It's like, because everything is software rendering, you can just run it to CPU and so on. In a standard game engine such as Unity Unreal, this is not how it works. A lot of things, including UI and animation and stuff, tends to be sort of incorporated into the main loop, making this very hard to work with in different ways. And there's also no unified representation of game rules and entities. It's really hard to figure out what you need to change. So neural game engines offers, to some extent, a way out of this, which is a really interesting way. On the other hand, they are very hard to author for. You don't have anything like the authorizability you get from a regular game engine, where you can go in and figure out, I'm going to change the behavior of this chair over here so that it has higher mass and that you can't walk straight through it, and it has a little bit more springiness and so on. So like the point of a game engine is that you can have a large team building a game, making very, very local, very exact, very predictable edits, which is kind of the opposite of like writing a prompt and see what a neural network comes up with. So I see these technologies as highly complementary. They're very different things, and they're both very cool. One idea for fast-forward models, and here we get back to reinforcement learning, is that you can distill them into low-res models that are actually really fast, and then you can fine-tune them on your own game. So if you have your own game in your game engine, you could take a generic something like Genie 3 when it's released, tune it on your own game, and distill it into something really small and fast. And this may unleash new ways of doing RL and planning in video games. But for now, I think these are ideation, prototyping tools, and it would also be really cool to do kind of like automated search in the space of game rules and game features. Which brings us to the next topic, designing. So basically, you think of reinforcement learning as like being intrinsically tied to playing. But what if we see the act of designing games or game content as playing? That's also a game, right? So we have this framework we call procedural content generation via reinforcement learning, PCGRL, where the basically idea is that you have an agent, the agent takes actions, the actions are to change the game as represented using representation, and you get a reward, and the reward calculation here is dependent on did this make the game better, which is a tricky question to ask. No, it's an easy question to ask, but it's a hard question to answer, and holds us back a little bit. This free Zoom meeting has ended. Whoever is responsible for the Zoom meetings. Yeah. Well, yeah, okay. Well, and anyway, so you train an agent for being able to generate a game levels. So here is, I don't know if you can see this well, because it's like, you think of a scan line in an old CRT TV. You have like an agent that runs through this level and keeps editing it all the time, and you're basically giving it instructions. This is the path length you should create, and this is the distance to the nearest enemy. So you basically have controls that let you change how it edits it. And these are some examples of different levels in this simple kind of little roguelike games that come out of giving the trained level editor different sort of inputs. So basically you can train a level generator that iteratively builds a level, and then you can give it like different inputs, this editor, and you get new levels really fast from it. Training is very slow, inference is very fast, as is common in reinforcement learning. We've also done this in 3D environments. Here is Minecraft is just a rendering engine for this, but basically building 3D little mazes and levels that have very specific functional properties, like you should have a clear path from the entrance to the exit. There should be two sort of treasures at side paths and so on, and the editor does this. And the nice thing about it is that because it does it bit by bit, it basically iteratively changes the world one tile at a time. You can collaborate with them. You can basically take turns with the editor. You can change things, and then you can run the editor, or the editor made a prototype where the editor suggested changes based on what changes you had done, and so on. So you can reinforce and learn it to basically be a good collaborator. I'm going to shoehorn this into reinforcement learning because it kind of is, because reinforcement learning is anything that solves a reinforcement learning problem. Map Elites, which is kind of the poster algorithm in the quality diversity algorithm family, is an algorithm that is an optimization algorithm that finds not a single solution, but a wide set of good solutions that differ according to some benchmarks. So basically, we've applied this to, for example, searching for Super Mario Bros. Levels inside inside a GAN, in this case, that is trained on a lot of Super Mario Bros. Levels. So you can basically use an automated playtest and search for levels that are playable and have a small number of enemies, few number of enemies, small number of high tiles, large number of high tiles, or large number of enemies, or enemies that where the agent uses few mechanics while traversing them. There's very few mechanics; you just run straight forward. Or those that the agent needs to use a large number of mechanics in order to traverse. So you can sort of, and you get this wide set of levels. Now, you can use this method to not only search for levels, but to search for level generators as well. And here you can use various interesting representations. One we're really fond of is called neural cellular automata. If you know cellular automata, a neural cellular automata is a cellular automaton, but implemented as a neural network, so continuous and nonlinear. Another way of seeing it is that it's basically the same level of a convolutional network again and again and again and again. So it's few parameters, and you can search for these generators. So what you're seeing here is the process that designs a level according to specifications we've given it. The process is absolutely weird. We have no idea what's going on. It's super strange. This is not optimized for like working with. This is not a good collaborative partner, but it's an efficient level designer that we find through this process of searching for different level designers that design levels with different context. How far can you take this? How far can you do reinforcement learning to find game designing algorithms or game generating algorithms? We don't know. There's a bunch of issues with this. The big issue is that you need to somehow estimate how good the content is, which is a very tricky problem and tends to be very domain specific. And then, of course, this usual reinforcement learning problem. It's just compute heavy to train. But I think that's another interesting frontier for reinforcement learning in video games. Okay, finally, adapting. What does adapting a game mean? You have a game and you want to change it in some way. Probably you want to make more money. I mean, this is why people adapt. Provocative statement. A/B testing is reinforcement learning, kind of. If you're in the game industry, you know what A/B testing is. Otherwise, you may or may not know. Basically, it is the very common, ubiquitous practice of if you have a game, particular free-to-play mobile game, but also other types of games, you basically serve different versions of the game to different customers, randomized typically, and you change small things like, hey, the starting screen, should you have like a smooth texture or a patterned texture, for example? And then you do all these changes randomly, and you observe what works, and you update your game like that. Zynga, with Farmville back in 2010 or 2011 or something, they're often seen as the pioneer for this kind of work. They A/B tested everything, and people in the game industry say that this was terrible, and this is not how game design should work. And then they saw how much money Zynga made, and well, you know. Essentially, this is a kind of reinforcement learning, right? You're taking actions. The environment is all your customers, and then you're adapting based on feedback. Is this do various large game studios actually use actual reinforcement learning, TD learning, something for this to automate this? I don't know. It's just the thought occurred to me that I don't actually know what's the algorithmic focus on this. This is the kind of stuff that is often not published for various reasons. One of them is the games industry, where if you publish these kind of, games industry tend to be very secretive, tend to not want to talk about their stuff, tend to not want to show anyone the data sets, what's in their data set, that they have a data set. And there's also the thing that a lot of people inside and outside the game industry might actually get angry if you tell them that their beloved game and experience comes about through TD learning. You know, they were like, no, this is wrong. You shouldn't do this. So therefore you don't publish it. But I'm happy to, please come speak to me if you know, if you're doing this or you tried it and it didn't work or something. Ad placement is probably reinforcement learning. I know that ad placement is reinforcement learning in other places, probably is in game engines as well. I don't know. AI directors could be reinforcement learning or could be reinforcement learning-ified. So here's a screenshot from Left 4 Dead, which is a standout 2008 title. How many of you played it? Good, good. It's a lot of fun. You survive a zombie invasion and you play with a bunch of, you play in a squad of 4 people. There are many things that make the game so good, but the one that got all the attention is the AI director that basically cycles you through phases. Basically, they have a target tension curve, how much tension you should be under, that they want to vary. So they want you to basically have like 30 seconds of hardcore actions and 30 seconds of like of downtime again and again and again. And to sort of accomplish this, the AI director moves with between states of build up, peak, and cool down to sort of, and build up is where they basically just like give you lots of more zombies, and cool down, they sort of stop the zombie tap. There's a Left 4 Dead 2 introduced a number of other things, procedurally changing the environment a bit based on this and so on. But as far as I know, this is all manual design based on lots and lots of playtesting. You could tune this with reinforcement learning as well, based on player feedback, right? And it would be an interesting thing to do. Again, I don't know if anyone has actually done it and not told the world about it, but definitely another reinforcement learning application. Now, this takes us all the way forward to this. It's an old paper of mine, Experience-Driven Procedural Content Generation. So Yorgos Yanakakis and me, where we basically lay out a vision of what if you have a model of given a particular player and a particular game and a particular game situation or level or something, you have an estimator of how good this content or what experience that content would bring in about in a player. You change it and you generate new content to sort of bring about the experience you want in the player. More concretely, here's old work of ours that is basically what we did here is that we had a Super Mario Bros. Game. We had people play versions of these levels, and then we had 2 different versions of the game. And you ask people, okay, which of these 2 levels is more frustrating? Which is more fun? Which is more challenging, etc. Feel free to take a seat. And then you do this with a few hundred people, and you look at like the playing style, the characteristics of the level, and what they answered. So then you can learn a model of, given this playing style and this level, they would think that this level would be really challenging but not frustrating, for example. And then you can simply search in this space. Search in level space for levels that, for example, I can look at like for any particular one of you, basically, that, oh, I know your playing style. Now I can search for a level that is maximally frustrating and minimally engaging, or the other way around. Is this a reinforcement learning problem? I would argue it is. We did this all with evolutionary algorithms, but evolutionary algorithms are often great reinforcement learning algorithms. Other provocative statements, maybe not provocative anymore. Really depends on the situation. But this is like something you could do much more of. This is kind of research. We built a whole typology about this, about like different ways you could do this. But it's really hard to do this research at large scale because you need like lots and lots of players, player data. So if you're not an actual game company, this is hard to do. All right, and I'm just about hitting the time limit with maybe 1 or 2 minutes left for questions. This is me. We just came out with a second edition of this Artificial Intelligence and Games book. If you're interested, you can buy it. You can also access it for free on this URL over here. And here's a procedural content generation book. I also write other books for free. I don't know why. But anyway, that's it from me. Do we have any time for questions? Do we need to move to the next?
Yeah, a
few minutes. Assertions, objections? Yes?
You asked whether the reinforcement learning game engine was efficient.
Right.
With respect to what resource?
Compute, like CPU, GPU cycles. Game engine, and the one from Fruchter's team and so on, the one that implemented Doom, it's arguably not efficient because it takes a whole modern GPU for inference in real time, and original Doom runs on 1993 hardware. I don't know the exact specifications for Genie 3, but it's probably a similar relationship. It's like, you use way more cycles to render the same thing. But I've heard that, and it makes total sense, that you could just downscale this to a tiny image, like 64 by 64, and preserve a lot of the actual physical dynamics, and then it would be fast. So that's why the statement about could you get this, maybe run this much faster than the game engine? Because again, game engines are architectonically unsuited to reinforcement learning research. Other? Yes?
You're talking about building the game content to maximize player satisfaction.
Yes.
How can you define that? Like in a task, how do you know that player is much more like?
You ask them. You ask them. So basically, that's something that particularly my friend and collaborator Yorgos Yanakakis has done a lot of work on, in protocols for this. Basically, you can ask them after the play session. You typically want them to have a preference choice, like which one of these two play sessions was more interesting, which one was more funny, which one was more surprising, whatever. And that's how you get fairly reliable stuff. Likert scales, where you select on a scale from 1 to 10, how much, how fun was this, and typically not so reliable. There are other things you can do. You can also do post-report, you can basically watch the video you have and then basically have a little wheel where you basically annotate your engagement level during the play session and so on. There's a bunch of protocols that work well, and there's more protocols that don't work. So it's like if you're ever been at the emergency room and they give you this kind of scale from 1 to 10, how much pain are you in? I don't know if this happened to you. It's happened to me. It's absolute bullshit, because what do you mean? What is a 10? Which is literally, I don't know. Sometimes you have to redefine that scale. Yes.
It seems not so sample efficient.
No.
You're training on RL.
Yeah. It's that. That's the thing I said in the end. That's why we haven't really taken this protocol to modern games and more complex content and so on. It's not sample efficient. You kind of need a scale of a real game developer or Google or whatever. Yeah.
What do you think of the difference between world models and for example, graphics simulator? Because recent
What was the other world models and
simulator.
right?
Yeah, it's perfect.
Yeah.
I'm asking because recent works in world models, for example, Genie and Oasis, they just remove the real world modeling and also simulation modeling. The typical world models, even in Ireland, they focus only on this dynamics modeling. It feels they are just doing trying to recreate simulations. Do you know that?
Yeah. So Genie 3, you could see it as like recreating a simulator, right, in a sense, or like a whole range of simulators, right?
Yeah, I'm just wondering, I mean, would the up bound of this world model be a simulator?
I mean, you can use it as a simulator. You can see it as a simulator. Whether it is a simulator is more, I don't know. A more interesting question is perhaps, is it a good idea to unbundle the world model and the reward model? And I don't have a good answer to that. Because it really depends on what you're trying to build. Because it is true that if you perhaps create a new environment in Genie 3, for example, and you want to use RL in that environment, then you still need another model to figure out your reward. And then you need to learn that, or you need to sort of find some generic model that looks at the pixel output and tries to figure out if this is reward state or not. I still think it's probably a good idea to separate these two, but I'm not sure. Okay. Thank you.